So HDFS is not really a file system. It's an organizational structure on top of a file system. So locally on your nodes, you're still running NTFS or whatever your local file system du jour is on your Linux box or your Mac box. Right? Your local file system is still there. And keep that in mind because there are some interesting aspects that will come in later on in this talk. So they will take these blocks and push them out. And they will start to actually replicate them. So the default replication factor is 3. So they will take blocks and move them around over the nodes inside the cluster. All right. And let's think about for a moment about their policy that they're using. So what they're doing is they first of all try to create the first copy local to the node that actually is creating the file. Why are they doing this? Well, now you have data locality, right? And data locality allows you to write performing apps. Great. Second copy is moved to a node inside the same rack. The reason there is like we actually want it to be redundant, but close by. Right? So it's like we're reducing network traffic to actually achieve this. And then the third copy, to create a quorum, we actually push down to another rack or to another even geo-distributed center, depending on how you set this up. So that is your copy for real redundancy in case your rack burns down, right, or your data center goes down the tubes. All right. That's the standard policy that they have in place. So their objective is not just availability. Right? While by doing this, they're actually thinking about it's like how we load balance, how we get fast access, and how we have fault tolerance. So in order to talk to an HDFS node, we actually have some participants. First of all, we have a name node, and we have a collection of data nodes. The name node, you need to figure out where are my blocks. And if you take a big block, big file, and start chopping it up in 64 megabyte chunks, you now need to figure out, it's like, where do they live? Well, they live on some data node. And it's the name node's role to actually figure this out. In the current Hadoop environment, this actually is a single point of failure. We'll talk about that later. There is a backup of that, which checkpoints into this, that reduces the risk to some degree, and they're working on making this automatically fail over. So how does that work? So we have the name node, talks to the backup node, and the name node, through heartbeats and balancing and replication, that's all the tasks that it does, it keeps track of all the data nodes. And just keep track while you're watching the slides on the coloring. It's like I'm trying to do it with colors, so it's like you can see where things are moving around. So we'll start to move things around if things start to fail. Okay? So the data node writes to the local disk. Again, the local disk was just your regular local file system. All right, so HDFS is an organization on top of that. So what does it take to actually put some files onto HDFS? Well, you take your file, right, you talk to the name node. The name node says, it's like, oh, it's like you have a replication factor of 3. That means it's that you need to go talk to these guys. And then, what happens after that? What a lot of people thought when I actually did this presentation a couple of times is like they thought it's like, oh, the writes go through the name node. No. Right? Now it's like the HDFS client actually talks to the data node directly. Right? He only uses the name node to figure out where to go. So he uses it as a directory, asks for directions, and then pushes the files out directly. Okay, so the next block, you will go and rotate that out and move these things around. So that's how we actually keep pushing things onto the file. Same thing for getting files. So if you get files, you have the reverse problem. Right? You now have a set of blocks. You don't have a big file anymore. Right? So one of the other things that you have to realize by using HDFS is that this is a write once, read many times optimized environment. Right? It's really optimized for getting and streaming through this data. Right? And scanning through the data. When do you do scanning? Well, it's like that's why data warehousing projects are very well suited for this environment. All right, so if we need to get a file, we'll talk to the name node, figure out where the blocks are, and talk directly to the nodes to actually get the file back to the HDFS client. So let's talk about failures. Right, we said it's like it was designed for failures, so it's like disk types, DataNode failures, it's like recs can fail, name nodes can fail, data centers fail. It's like I know all about it. It's like one of my team, part of my team actually was in the directory. We were part of Office 365. So I've seen all of these failures happen. To give you a small anecdote, it's like disk failures. So at a certain point in time, we experienced massive disk failures all at once in our data center. Anything special? No, it happened to be that we bought 1,000 disks at one shot. And they literally all failed within 2 weeks of each other. Hi. Shit happens. We'll write that on the recording later. All right. So how does HDFS actually deal with this, right? Because it's like it says, like it knows about all these failures. So what if my data node fails? So it's the name node who actually detects that my node fails. And as soon as it does, it will actually instigate a new replication. So it will take, so what was on the, so black, green, and orange. Right, it dies. Name node knows that it's dead now and needs to start replicating this information. Find yourself a black box, a green box, an orange box. Replicate it so you have a quorum. So it reestablished the quorum based on the number of nodes. This is why you need more than 3 nodes. Right, having an Hadoop cluster with just 3 nodes is kidding yourself. Right, you really need something bigger to be fault tolerant. Right, that's the same thing as like if you have a RAID array, it's like you need something bigger than that. So what if the name node fails? Well, it's like you can, right now you need to manually fail over to your backup node. They're working on actually making this automagic. That's work that they're doing in the Apache Foundation right now to actually do this. Now more interesting is like how do we deal with rebalancing and scaling? Because this is a pizza box environment, and one of the things that we want is to be able to add pizza boxes or repurpose the pizza boxes depending on our loads. Well, that's the whole promise of this. All right. So what if we add the node to the system? Name node will detect that it actually is there. It will then figure out it's like what to do. It will take some blocks that it can reparent, and it will start moving things around and rebalance the system. You don't have to think about this, which is the beauty of this, right? Because it just moves blocks around. So in summary, so HDFS is the underpinning. It's literally built to deal with thousands of nodes in parallel. What you can achieve here is that you can create a storage fabric, really, that spans terabytes to petabytes of data, right, in a very efficient way. So it uses a block size which maximizes, or optimizes, I should say, for sequential scans. And that's something you have to keep in mind, right, because that on itself already says something about the application of this technology, right? As I said, I'm trying to learn you how to fish. So they don't need to use expensive storage technologies like mirroring or RAID, because it's built into the software. They just depend on SATA disks. Right? They're happy with that. They assume failure, they will deal with it. That reduces your cost. Right? And there is one downside to this. Because since we're splitting it up in blocks, right, you don't really have this higher level abstraction that you can deal with. Now it has one huge advantage when it comes to processing over sequences, because we can push it through the data nodes, as we'll see in a moment. So how do we work over this? Right? How do we actually deal? So now we have petabytes of data in a distributed storage system on a bunch of nodes, right, which all have CPUs locally to the disk. Right? How do we leverage this? This is where MapReduce comes in. So MapReduce is nothing more than a programming framework. Right, last year is like the last year, I worked for Eric Meyer who you might know is the guy who created Link. And so we were working on these functional programming languages and how they actually fit into MapReduce. Because one of the things that MapReduce does is like it actually allows you to compose a mapper function and a reduce function that you then will distribute to all your nodes. What is one of the characteristics of a MapReduce pair? It has to be code that has 0 side effects. Which is why it's like MapReduce and functional languages sort of like go hand in hand. Because like, you cannot write a mapper function that constantly goes to some central location or changes some state somewhere, because like you have thousands of them running in parallel. That would basically bring your whole system down. Alright, so a mapper and a reducer have to have 0 side effects. So it's a divide and conquer environment, right, in the mapper, and then you combine and reduce the results actually down. So that's the only thing that the user has to worry about, writing these two functions. The framework itself, which is also called MapReduce, will actually take those jobs, or functions, sorry, construct a set of jobs, hand them to the nodes, and execute them in parallel. Figure out if they're running, if they're done, if they're in error state, shoot them in the head if they're blocked somewhere, and restart them. So the first principle is like take a big problem and actually divide it into small pieces. Alright, so MapReduce actually is taking that, bringing it into a very small function, do some work on all your subsystems, and then combine the outputs and collect the results. Alright, that's what we're trying to achieve here. So the top part is called map, the bottom part reduce. So how does that fit into our Hadoop world? Well, it starts with the job tracker. Right? The job tracker is the master, and he has a bunch of slaves, which are called task trackers. Right? These task trackers actually are the places where you run the job right inside the JVM. Right? So the master actually keeps track of everything. It keeps the queues, it knows about scheduling, it knows who's online, it knows when task trackers are going dead or when they are added, and it knows when to check points for failures. Right. So it uses the same mechanisms as HDFS, surprise, surprise. Right. So the underpinnings in terms of figuring out who is there, are you still alive, all those things, the bookkeeping of the job tracker and the task tracker is the same as the name node and the data node. Right. So how does that now add up to, sorry, there's one thing actually, sorry, my slide got messed up. So that should be a little lower, my apologies. Those task trackers, when they write information, where do they write their information? They write their information to the local disk, not into HDFS. So if a mapper writes his output, or if a reducer writes its output, where is it? It's on the local file system. Why? Because HDFS is optimized for write once, read many. Right? And not for is like sorting, moving over, doing all sorts of temporary shuffling, etc. Right? So be aware that that's another thing. Is like, so your local the storage on your machine is used for two purposes. Participate in HDFS and be this big scratch pad for your MapReduce functions that are running on behalf of the task tracker. So how does this fit in? Well, we're actually pairing them up. So the name node and the job tracker are actually combined. All right? And every data node has a task tracker. So what do you see that we're doing here? We're actually bringing the compute local to the data. Right? If you cannot bring the mountain to Muhammad, right, we have to bring Muhammad to the mountain. And that's what we're doing here. Right? We're bringing the execution entity to the data because at the end of the day, it's too expensive to actually move the data. Right? Which is why it's like, it's also called MapReduce, right? It's like we're trying to do this locally, get to a smaller data set that we then can pick up and transfer around within the fabric. So the job tracker talks to the task managers. Right, the name nodes talks to the data nodes. And so let's look at how this actually works. So I created this artificial environment, right, where we have a MapReduce job that we're going to visualize. So I have 3 data nodes. On each data node, I have 2 blocks. Each block has 2 rows of data in it. Right? They look like rows, but they're just file records. Right? It doesn't matter. So we have 2 mappers, and we need to get the sum of sales grouped by zip code. Seems fairly simple, right? So let's go and do this. So the mapper is going to talk to the first block on data node 3, right? And the second mapper talks to data block number 2. Gets the information, feeds it in, and writes the outputs to the local disk. Right? So it's like we only see one bucket. Then we go to the second node, collect the information, right? And the third one. So now why did I choose this imbalanced picture? Right? Because like he would have said, like, well, it's like 3 data nodes, you should have taken 3 mappers. Well, I want to illustrate a point and about MapReduce here. So the point that I want to illustrate is that at this point in time, given where all the data lives, you cannot answer the question. And the reason why you cannot answer the question is that the yellow nodes are spread between the 2 storage locations. So I cannot do the sum grouped by zip code. Same is true for the green nodes. So a mapper, by definition, right, if data ends up between different nodes, it cannot be the only part of the answer. This is where the reducer comes in. So the reducer actually spits up the reduce tasks. And the key thing here, right, it's like if you go between here, it's like you see this, what does a reducer have to do? The reducer has to talk to every mapper to get the information. Then he can use the built-in sort mechanism into the framework. Sort is built in inside the MapReduce framework. Create the results and publish it and call it done. So that's how things flow. And this is a very simplistic example, but it sort of tries to illustrate the things that you have to be aware about. It's like that, although it's like those mappers are highly parallel, right, the reducer still need to talk to all these mappers. So the more data transfer you have there, the more expensive that part will be, which is why the map stage is, in general, more expensive than the reduce state. So let's talk about the actual number of tasks, therefore, that you need to create the optimal workload. Right, in a normal case, we would actually say, like, if we have, say we have 1,000 nodes, right? It's like we want to create a number that is much larger than that. Why? Well, the reason is that you are creating resiliency in your system. Right. What if somebody gets blocked and the task manager needs to shoot it and move it over to another node? Your restart cost is much lower if you have smaller jobs than if you have ginormous jobs. Right? So you have to think about that ahead of time when you construct your jobs, right? In terms of what is the size, how long is this going to run? And if you have long-running map and reduce tasks, in general, you should probably rethink, because your restart characteristics will push out your end result. Because again, failure will happen. Right? Now on the reducer side, you still have a skew problem. Right? On the mapper side, this actually increases your performance, but on the reducer side, you might have a skew problem, because like if the result set that is produced, in this case for a particular zip code, you might simply have more work to do there. And there's nothing you can do about that. So inside MapReduce, we deal with failures the same way. Right? We detect them by master pings. If a job fails, we reset it, give it to a different node. and then we try to stitch things together. All right. If the master fails, we need to restart the whole job. All right, that's the simple mechanism. So the key thing here is that we have a very simple set of rules and policies which make the world very predictable, but you have to realize them when you start to utilize an environment like this, otherwise you're working against them, which would be very, very counterproductive. So in summary, it's like it gives us a very high tolerant, fault tolerant environment. Right? It allows us to write jobs, effectively, that can be distributed to a large set of nodes, literally on thousands of nodes. Right? Reasonably easy to do this, work against large amounts of data, right? And the framework itself, not the code, actually removes a lot of complexity for the developer. Now there is one big downside. That this MapReduce function is actually the only one who knows about the schema. Because, again, this was a schema-less environment, right? It was going after this name value pair or key value pair. And so all that code is embedded. So the downside here is that we actually are facing a maintenance problem or a code sharing problem with regards to is like logic inside our application, which is a big challenge in general that we're facing. Just something you need to be aware of. The other thing is like we don't necessarily have a distributed or a declarative language. So let's talk about those. So what you saw so far is that we do everything to Java or JavaScript. Right? And when the Facebook guys and the Yahoo guys were actually starting to do this, they reached a different conclusion. They said like, hey, actually, maybe it would be better if we have a declarative language. And so they created Hive, which is coming out of the Facebook team, right, which is pretty much a SQL-oriented language with HiveQL. And then the Yahoo guys created Pig, right, which is more a procedural kind of query language. Regardlessly, it's like, that's what they use. But the key thing is, it's just the language abstraction on top of the MapReduce framework. So what do? They present you with think of it as a DSL, right, to express what you want to achieve, and they map it into a set of MapReduce jobs. So how does that look? Take this example. So we have two data sets. We have a weblog that has visits, right, where it's like we have a destination URL and we have ranking information, right? This standard business for Google and Bing and for advertisement agencies, etc., to figure out how these two things relate. So the query that we need to find is what is the source IP, right? So we can associate ad revenue to a source IP. That requires us to join information between two disjoint data sets, right? In a relational query, this would be easy. It's like select star from A and B, join on the page URL, and you're done. In MapReduce, that would look like this. I'm not going to use zoom it. I'm not supposed to read this. It is actually working code. The thing is, it actually takes us 3 MapReduce jobs to actually get these 2 joins done. Right? That's how it is. And that's a lot of code. And the downside is not that it's so much a lot of code. This reduces the number of people that we can actually use in this environment to create useful applications. Right. So how do we do this in HiveQL? Well, in HiveQL, it looked like this. Right. Select column list, right? Source IP, total revenue, average. And it's like we do a select from one source, from the rankings, and then it's like we're actually going to push this out and join this and create a revenue column. Okay? So the Facebook guys actually figured this out. It's like that MapReduce is like they could not use, and it's like if you look at it, I got this from one of my close friends who actually works there. Today, it's like of the 150 MapReduce jobs that they're running on a daily basis, So only or the 150,000, sorry, it's like only 500 are real coded MapReduce ones. The other ones are Hive queries. Right, to sort of give you a compare and contrast about how this is done. So what is the goal here? The goal is to actually use a declarative language that we can use to navigate over these massive data sets, leveraging the Hadoop stack, still working on Hive, right, but leverage it on MapReduce. So what it does introduce the concept of a table. Ta-da! Because you're writing a declarative statement, and the declarative statement needs to be bound to things like a column. Right? Unless you wanted to use some string, substring function. Right? So Hive actually is like, introduces a pretty interesting type system. It has the primitives as you might expect, but it also has some complex types, so it allows you to do in-bound array, for example, which you cannot do in most SQL languages today. Which makes it that you can do things much more easily. So let's look at how this actually translates. So we create a Hive table, which looks something like this. Create a table called sales. We have some information, and then we're going to say it's being partitioned, in this case by state. All right, so in the US, that would give you 50 files. Now, the thing is that is like, look at what they do. They actually indeed create 50 HDFS files, one for each state, and they remove the information that is the partitioning key and only store that once effectively because that's the file. So you won't see any evidence back that it's like, this is the Alabama file, this is the Alaska file, this is the Wyoming file inside the records anymore because they compress that out of the environment. Now underneath HDFS, because it's still HDFS, it's like HDFS shows you one big file per state, it's of course chopped in 64 megabyte chunks. So if you then want to go and execute this, right, you say, for example, this query, right, give me the sales, and what that will do is actually it will send out that query to all 50 nodes that have that file. Right, so it will go to the name server, it will figure out, it's like, oh, there are 50 places where this file actually lives based on the partitioning information. So I now have to send my query, my MapReduce job, sorry, to 50 nodes. Now, if I would restrict my query to only one state, it is actually smart enough to just figure out that you only need to send this to one node and go from there. The last one is actually that we can embed MapReduce functionality inside HiveQL. And what you see here, the Python CD mapper PI, is actually allows you to embed mapper logic into the SQL language. And that's a trend that you see is like in the industry right now, where it's like the two worlds are starting to come together pretty quickly. Whereas like we can start to add MapReduce functionality into the SQL language. All right,